Developers are wasting weeks building massive orchestration layers for problems a single, well-prompted model could handle in an afternoon. Building AI agents right now is plagued by a costly mistake, choosing an architecture based on what looks impressive rather than the actual task. Every design choice you make comes down to a strict trade-off between the capability of the system and the overhead required to run it. If you keep things too simple, your system is brittle. It breaks on edge cases and fails the moment it needs to adapt to new information in production. But if you swing the other way and deploy a multi-agent swarm for a straightforward extraction job, you introduce crippling latency and coordination headaches. This overengineering carries severe hidden costs. Every new agent you add exponentially increases the points of failure, and your API token bills skyrocket as models talk back and forth just to figure out who should do what.
Your goal is never to build the smartest system possible. It is to build the absolute simplest architecture that reliably solves the problem. To cut through the hype, we use a diagnostic framework. This chart maps system complexity against task success. By identifying the failures at the extreme high and low ends, we reveal an optimal starting point right in the middle. Selecting the correct pattern up front limits your overhead and ensures you don't have to redesign your entire architecture under pressure when real users start hitting it. This flowchart maps task properties to architectures. We begin right at the top. Is the solution path known in advance? If known, we ask if the workflow is fixed. Think of processing an invoice. Extract, validate, store, confirm. The steps are identical every time. This diagram illustrates the sequential pattern. For fixed workflows, you don't need complex AI orchestration. Deterministic code handles the sequence from raw input to final output, passing data directly. You only insert a large language model at the specific nodes where reasoning, interpretation, or text generation is strictly required. Everything else remains fast, predictable, deterministic code. However, the moment your task requires branching logic based on user input or relies on retrieving external information, a rigid sequence will break. That brings us to our next test. Can the task structure be articulated before execution begins? Even without specifics, tasks like writing a research report have a clear structural order. Gather data, synthesize it, and then write. This chart outlines the planning pattern. By breaking a complex task into a roadmap up front, analyzing, decomposing, and sequencing the steps, you expose dependencies early and prevent wasted compute. While this upfront roadmap reduces the prices mid-execution, it does introduce a layer of rigidity. If real-world feedback invalidates the initial plan, the agent will rigidly struggle to adapt. So, what do you do when the structure of a task is completely unknown in advance? This flowchart shows the react pattern, the standard solution for dynamic exploration. As you can see, it operates iteratively. The model takes a reasoning step, executes an action, observes the result, and uses that feedback to decide what to do next. To perform those actions in the real world, React sits entirely on top of the tool use pattern. Here, the central decision maker communicates bidirectionally with APIs, search engines, and databases to retrieve the necessary context. The primary failure signal you will see with React in production is excessive looping. When an agent gets stuck repeatedly visiting the same resolved questions, it means two things. It either lacks a clear stopping condition, or the task actually had a hidden structure that required upfront planning instead. React buys you maximum flexibility in dynamic environments, but it costs token efficiency. If the agent gets lost exploring dead ends, your latency and API costs accumulate quickly. Next, we evaluate your constraints. Does output quality matter significantly more than response speed? This diagram maps the reflection pattern. For tasks where errors carry heavy real-world consequences, this adds an essential layer of self-correction, looping from critique to revision before delivering a final output. The mechanical trade-offs here are steep. You are generating answers multiple times, guaranteeing higher latency and significantly driving up your token expenditure per query. For reflection to actually work, you must provide explicit, verifiable criteria for the critic. Without a clear grading rubric, the feedback loop is completely useless. That brings us to our final test. Does the task require domain specialization or a scale that a single agent physically cannot handle? This graphic demonstrates the multi-agent architecture. When workloads are too large for one context window, a central coordinator routes distinct parts of the job down to specialized subagents.
Splitting the workload introduces shared state complexity, difficult routing logic, and compounds your system's failure points. Because multiple agents exponentially increase your orchestration overhead, they must be treated as a last resort, never your default starting point. AI architecture is an evolution. You graduate to complex systems only when simpler ones explicitly fail. For the pragmatist developer looking at 80% of real-world tasks, a single agent utilizing tools and the React framework is the perfect starting point. It provides inexpensive failure detection and allows for rapid iteration without orchestration bloat. If you are acting as a quality controller, you should only layer on the reflection pattern for high-stakes deployments, like client-facing code. Keep in mind that this approach sacrifices speed, making it completely incompatible with live, high-throughput systems. Finally, for the enterprise scaler, multi-agent swarms are strictly reserved for massive operations that exceed a single context window. Your primary engineering focus must be on deterministic routing rules. If you rely on an LLM to reliably route everything, your central coordinator will fail. Ignore the hype cycle. Let the actual failures of your system dictate when it is time to add complexity,